Alright, so let's look at part 3, day 1. We'll start with a question. Why do nurses and doctors typically measure a patient's blood pressure more than once when performing a physical? So, one answer may be that averages are less variable than individual observations. So maybe they're trying to get a more accurate reading by looking at more than one. So now let's go ahead and look at the mean and the standard deviation of the sampling distribution of X bar. So last part 2 was all about proportions, sampling distributions of p hats, and the difference here is that this is sampling distributions of X bars. So the mean mu sub X bar is equal to mu, so that's pretty similar to what we saw before. Oh, that is an ugly equal sign. And then standard deviation is a little bit different. So the standard deviation of X bar is equal to sigma, the population standard deviation, divided by the square root of n. If you don't know the population standard deviation, then you'll substitute in S, the statistic. So this is as long as the 10% condition is met. So just like before, we have to make sure that we can prove, or at least verify, that 10 times the sample size is included within the population. So, notations, just kind of going over these again, make sure that we understand. Remember that this is the mean of the population. This is the standard deviation of the population. P is equal to the proportion of the population. P hat is equal to the statistic, the proportion of the sample. X bar is the mean of the sample. Mu sub p hat to the mean of the sampling distribution of p hats. This is equal to the standard deviation of the sampling distribution of p hat. And mu sub x bar is equal to the mean of the sampling distribution of x bar, basically the mean of the means. And then this is the standard deviation of the sampling distribution of x bars. All right, let's look at number 13. Suppose the number of movies viewed in the last year by high school students has an average of 19.3 with a standard deviation of 15.8. Suppose we take an SRS of 100 school students and calculate the mean number of movies viewed by the members of the sample. What is the mean of the sampling distribution of x bar? So we know that mu sub x bar is equal to mu. We have two different numbers here. We have the standard deviation and we have the mean. So we know that this mu sub x bar is equal to 19.3. What is the standard deviation of x bar? So you always have to check for the 10% rule first. So take the sample size 100 times 10 equals 1,000. You're right, it is safe to assume there are at least 1,000 high school students. Right, and that would seem reasonable, especially if you're talking about, it doesn't say in the US, it just says high school students in general. Alright, so then we find the standard deviation. So sigma sub x bar is equal to sigma divided by the square root of 100. So sigma is equal to 15.8 divided by the square root of 100, which is equal to 1.58. Alright, so let's look at sampling distribution of a sample mean from a normal population. Suppose that a population is normally distributed so gross. Is normally distributed with mean mu and standard deviation sigma. Then the sampling distribution of x bar has a normal distribution.
No.
Sorry, we can be quiet today.
Cancel timer.
Has a normal distribution with a mean mu and a standard deviation of sigma divided by the square root of n. Provided the 10% condition is met. Alright, so at the Peanutty Peanut Company, dry roasted shelled peanuts are placed in a jar by a machine. The distribution of weights in the jars is approximately normal with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding that the contents weigh less than 16 ounces, or randomly selected 10 jars and finding that the average contents weigh less than 16 ounces. So if we think about this for a second, since averages are less variable, than individual measurements,
Ours are choppers. We can't plant it. Really? Yep.
I would expect the sample mean of 10 jars expect the sample mean of 10 jars to be closer on average to the true mean of 16.1 ounces. Thus, it's more likely that a single jar would weigh less than 16 ounces than the average 10 jars to be less than 16 ounces. So one jar, you might get one that's more than, less than, but you're going to have a lot more variability. But if you got 10 jars at a time, on average, their average will be closer to the mean. Alright, so now let's look at part B. So let's divide this in half. We're going to do this two ways because it wants us to find each event. And so first, for both events, we need to describe our variable. So let x equal the weight of jar of peanuts. Okay, so we need some information. We need to know what x is equal to, 16. We need to know what the sample or the mean is, 16.1. And we need to know the standard deviation, which is 0.15. So we can find the z-score, which is equal to 16 minus 16.1 divided by 0.15. So this will equal negative 0.667. So now we'll find the area of the curve. So we'll have 0, negative 0.667, and we want greater than, we want less than. So normal CDF from negative infinity to negative 0.667, and standard deviation is 0 and 1, and we get 0.2525. Right? So we have a 25% chance of selecting a jar of peanuts that weighs less than 16 ounces. So then, for the second event, we're going to let x equal the average weight of 10 jars. Alright, so we're going to have z. Well, first, we need to find our new mean and our new standard deviation. So mu sub x is equal to mu, which is equal to 16.1. And now we need to find our standard deviation, which is equal to sigma divided by the square root of n. So this will be 0.15 divided by the square root of 10. So we get 0.047, right? Provided that the 10% rule is true. So if we look at the 10% condition, it is safe to assume there are at least 10 times 10 equals 100 jars of peanuts in the population. Alright, so now we're ready to find the z-score. So the z-score is equal to 16 minus 16.1 divided by 0.047. So we get negative 2.13, which we can tell is going to be a lot smaller area. So if we draw a curve, here's 0, negative 2.3, and then less than. So do our normal CDF, and our area is going to be about 0.0175. So you can see that there's a much smaller chance of getting an average of 10 jars of peanuts that have less than 16 ounces in them versus one single jar. Alright, so let's look at number 15. A grinding machine in an auto parts plant prepares axles with a larger diameter, mu equals 40.125 millimeters. The machine has some variability, so the standard deviation of the diameters is sigma equals 0.002 millimeters. The machine operator inspects a random sample of 4 axles each hour for quality control purposes and records the sample diameter x bar. Assuming that the process is working properly, what are the mean and the standard deviation of the sampling distribution of x bar? So the mean, mu sub x bar, is equal to mu, which is equal to 40.125 millimeters. The standard deviation, so we got to do the 10% condition. It is safe to assume there are at least 4 times 10 equals 40 axles in the population. Okay, so then we do sigma sub x bar is equal to sigma, which is 0.002 divided by the square root of 4, which is equal to 0.001 millimeters. So, here we go. So how many axles would you need to sample if you wanted the standard deviation of the sampling distribution of x bar to be 0.005 millimeters? So basically we're using our formula and we're going to solve for n. So 0.0005 equals sigma 0.002 divided by the square root of n. So start by squaring both sides or multiplying by the square root of n, it doesn't matter. So let's just multiply by the square root of n. So we'll have 0.005 square root of n equals 0.002. So divide both sides by the square root of 0.005 and then square both sides. And that will give us a sampling size of about 16. So always round up. It's actually 4, and then once you square the 4, you get 16. So we need to have a sample size of at least 16. A car company has found that the lifetime of its disc brake pads varies from car to car according to a normal distribution with a mean mu equals 55,000 miles and a standard deviation sigma equals 4,500 miles. The company installs a new brand of brake pads on an SRS of 8 cars. If the new brand has same lifetime distribution as the previous type of brake pad, what is the sampling distribution of the mean lifetime x bar? So we're going to find mu sub x bar. Mu sub x bar is equal to mu, which is equal to 55,000. In order to find the standard deviation, we have to do the 10% condition. So it is safe to assume there are at least 8 times 10 equals 80 brake pads in the population. So sigma sub x bar is equal to sigma divided by the square root of n. So that would be 4,500 divided by the square root of 8, which is equal to 1591 miles. All right, part B says the average life of the pads on these 8 cars turns out to be x bar equals 51,800. Find the probability that the sample mean lifetime is 51,800 or less. All right, so we already have our mean and our standard deviation from above, so we're ready to go ahead and find the z-score. So we want to know the probability. Well, first let's find the z-score, which is 51,800 minus 55,000 from above divided by 1,591 from above. And that gives us a z-score of negative 2.01. So now we're going to normal CDF. Right, zeros here, we're talking about the probability that z is less than negative 2.01. So negative 2.01, and we want to shade to the left. So the area, we do normal CDF, negative infinity to negative 2.01 with standard deviation, mean and standard deviation of 0 and 1. So we should get 0.0222. So what conclusion would we draw? right? Because this is less than 5%, we would be surprised if the company's claim were true. So we're going to doubt the company's claim basically because it's less than 5%. All right, so our assignment is down here at the bottom. Oops. We're going to skip that last problem. We'll do it tomorrow in class. There's an error on it. So let's go ahead. If you're going to be gone tomorrow, then we're going to do the problems at the end of section 4. Into section 7.3. And we're going to do problems 49 through 55 odd. All right. If you're going to be in class tomorrow, then we'll do the last problem here on our notes, and then we'll have time to do these 4 problems in class.